No other weather phenomenon has shaped human existence more than drought. Drought is the largest and the longest lasting and the deadliest form of weather on Earth. But drought doesn't kill you by drying you up. The way drought kills you is with war, with mass migration, and with famine. I want to talk about that from a global perspective as we get this lecture going on drought. But take it to Africa. You see, between the Saharan Desert, which is here, and the tropical rainforests of Central Africa, there's this region called the Sahel. And the Sahel has been undergoing something called desertification. You can see the definition of it right up here. Basically, desertification is the expansion of a desert into a region that was maybe semi-arid before that. You see, tens of millions of people live on the boundary between the rainforest and the Saharan Desert because this was once very productive region in terms of agriculture. But I'm going to show you what happened. You see, the graphic that's in the top here shows you something called the Sahel Rainfall Index. And zero value on this represents average. So you can see that average is really found by having some years that are wetter than average and some years that are drier, and they all kind of average together to give you the zero line. Beginning in 1970, though, there was a major climatic shift. And what was happening was the Sahel was undergoing desertification, the becoming of a desert. And the Sahel Rainfall Index showed many, many years in the 70s, 80s, 90s, and even to today where they were far below their average rainfall. And this caused major problems. This caused war, this caused migration, it caused famine, it caused issues because people didn't have the water they needed to grow the crops they needed. They didn't have water to drink. They didn't have water to survive. One of the largest lakes on Earth, well, formerly, Lake Chad, shrunk from what it once was down to this very, very tiny little mud puddle that's left now. Can we blame this on changes in Earth's climate? Absolutely. Can we blame this on human overuse of water through irrigation? Yes. These shifts happen, but because these shifts happen in regions where there are tens of millions of people, well, we see the major, major problems that it can cause. When this was going on in the early 1980s, several pop stars, including Michael Jackson, got together, like Michael Jackson, Lionel Richie, and many, many more, got together and sang a song about it. And they sang a song called We Are the World. I'm sure you've heard of it. Very, very successful single. And when this particular track came out, it was done to raise awareness and raise money to help with the relief in Africa. And so that song originally sung because of a drought. So this is just a screen capture from the video. I'd like for you to watch it. I'll post it for you so you can watch it. Okay, let's talk about the money aspect of this. Now, I live in Champaign County, one of the most productive counties in the world, one of the most productive regions in the world for producing major row crops like corn and soybeans and wheat. Now, when you look at this, I want to talk to you about the financial aspects of a drought. That chart that's at the top there, this is a chart that if you're studying economics or finance, you probably see a lot of these. This is the price showing a chart showing the price of a commodity, corn. Now, when you look at the y-axis, it's actually telling you the price per bushel. What's a bushel? It's a basket, okay? It's like a basket. It's a unit of measurement for corn and soybeans, okay? Now, from mid-2009 all the way to almost 2013, we're looking at the price. And so the price kind of is the low price and high price over a certain time period. Now I want to show you something. If you're a farmer in central Illinois and you have 1,000 acres, that's a pretty normal size farm, okay? 1,000 acres, if you're growing all corn, well, every single penny move in the price of this commodity, penny per bushel, is worth $1,000 in profit or loss to you. So why are we talking about this? In 2012, in the middle of summer, a massive drought turned our corn into what you see down here. And the price of corn went from nearly $5 to $8.50. Now, if you study economics and finance, I'm sure you've already figured this out. For the rest of us, yeah, that's a $350,000 profit per farmer if the corn would have come in and you'd have had it to sell. But a lot of fields in Illinois are not irrigated. We usually don't need to irrigate our fields, which means we took a massive, massive insured loss. That's a huge hit to the economy because of this. So farmers, thankfully due to insurance, were covered. But if they would have had corn to sell and the price jumped that high, $350,000 in profit to each 1,000 acres of corn. Oh, and we have 12 million acres of corn in this state. Something to think about there. By the way, after that happened, so here's the peak I just mentioned. This is what 6 phenomenal years of weather due to the price of that commodity. It is trading in the basement. It's at nearly all-time lows. it might be a good time to invest in corn. I invest in it. There's an ETF that is called corn, and you can buy a share of it right now when I'm recording this video for about 17 bucks. It's been historically as high up here as $60. So just a little bit of trading advice for you. Now remember, I'm recording this in July of 2018, so I don't know what's going to happen after this, but it's something to at least think about there. All right, I'm going to take you to Tokyo, Japan. Massive, massive city here, right? What would happen this year if Tokyo only got 20 inches of rain? Just 20 inches of rain. Well, Tokyo would have one of its worst socioeconomic droughts ever. Why? Tokyo annually receives about 60 inches of rain. If it only got 20, that's a third of its yearly rainfall. This would cause massive, massive problems to this huge city. Compare it to Cairo, Egypt. What if Cairo got 20 inches of rain this year? Well, if Cairo, Egypt got 20 inches of rain here, we would be rewriting Genesis chapter 7. Because annually, Cairo gets about 2 inches of rain. 20 inches of rain, 10 times normal, would completely flood the city and reroute the Nile River. It'd be incredible to see that. Now, why am I bringing this up? I'm bringing it up because it's the first note I want you to take down. There is no formal definition of drought. You see, drought is region specific, so there's no formal definition. You can't say, well, if you only get 75% of your rainfall, then you're having a problem. It doesn't work that way, okay? It's region specific, so there's no formal definition. But remember this, it is the #1 weather-related killer worldwide. Weather-related killer worldwide. It's the largest weather disaster we have on Earth, and it's the longest lasting type of weather disaster we have on Earth. And basically, we like to break it down into 4 main categories. We have a meteorological drought. That's a long time period of below normal precipitation. But remember, that's region specific, so it means something different for Denver, Colorado than it would for Chicago, Illinois. Hydrological drought. This is when we see a drought where we're getting a deficit in groundwater or stream water, which means we could get plenty of rain, but our groundwater supply, because it may be supplied from an aquifer or something else, could be depleted, and that can cause a hydrological drought. Agricultural droughts are often the first type to set in because our plants respond very quickly to not getting water. So we can often look down from space with our satellites and see where we're seeing stress due to agricultural drought, because the plants, well, they wilt very, very quickly. The one type we're going to talk about, and this is the picture that you see in the background here, this is socioeconomic drought. When you have a socioeconomic drought, you have all 3 of the preceding types, meteorological, hydrological, and agricultural. And it's so bad that we now have reduced water for human consumption in all types of ways. So when you look at this, that Dust Bowl of the 1930s, one of the worst weather disasters to ever hit the United States. In fact, arguably the one weather disaster that has shaped U.S. history more than any other type of weather, well, that came through as a massive, decade-long socioeconomic drought. We'll finish this lecture talking about it. Now, oftentimes in the middle of massive droughts, we have heat waves. And I'm going to take a break from my discussion here on drought to talk about heat waves. We really want to talk about the impacts on humans. So I introduced you to a chart here. It's called the heat index chart. Now, what is the heat index? Well, it's an apparent temperature. What does that mean? Well, as humans, we stay cool by sweating, okay? Now, we actually have other mechanisms we can stay cool by. If the temperature, listen carefully here, is below 95 degrees Fahrenheit, you can stay cool by radiatively cooling. That's where the heat energy of your body leaves in, as thermal infrared radiation, like we saw back in the satellite lectures. So you can cool off that way. You can cool off also by conductively cooling off, which means if your skin is hot and the air is cooler than your skin temperature, well, you conduct heat into it. You can cool off convectively. Okay, that's where your skin produces warm little blobs of air, and this is kind of amazing, but it does this, that kind of just advect or convect off of your skin. You can also cool off by sweating. That's our primary mechanism for staying cool. Now, if the temperature is below 95 degrees, you can cool off by all 4 methods. Above 95, you can't cool off radiatively, you can't cool off convectively, and you cannot cool off conductively. You can only cool off by evaporation. And because evaporation, the rate of evaporation, is controlled by how much moisture is already in the air, listen carefully, the higher the humidity, the more difficult it is to get the sweat to evaporate. Now, what does all that mean? Well, as the temperature increases and the relative humidity increases, the rate of evaporation of water, being sweat, off your skin slows down. And therefore you feel hotter and hotter and hotter. So they came up with an equation that helps us understand that to give us this apparent temperature. And let's get some use out of this. 98 degrees outside with a relative humidity of 60% means it feels as though it's 123 degrees outside. That's the rate at which your skin is trying to cool itself off, as if it's 123 degrees. And why do we care about this? Well, our ability to stay with our body temperature at 90 degrees is important for functionality. When it starts to get hot and humid, we can go through fatigue, sunstroke. We can actually have heat stroke. This is where the body shuts itself down and blood flow becomes a problem, starving parts of our body, especially our brain, from oxygen, and can potentially kill us. So you must be very, very careful when the temperatures increase and the humidity increase because of how the body cools off. And one important point to make here, when the heat index was created, it's valid only in the shade. So if you're standing in the direct sun, this is an underestimate of what it feels like. And remember this, it's assuming a 5-mile-an-hour wind, which means if there's a breeze, that helps the sweat evaporate, which means this is an overestimate of your temperature. But again, heat waves sparked by hot, humid conditions take an enormous toll on human lives. And that's what I want you to remember from the beginning part of this lecture. The deadliest form of weather in the United States over the last 30 years is heat. Heat doesn't kill you by getting you too hot. Heat kills us with heat-aggravated illnesses, like asthma as a good example of this. People that have asthma, when it gets hot and humid, can't breathe. They go to the ER. Heat also hits certain populations harder than others. What do I mean by that? Well, it tends to hit elderly people, poor people, and it tends to hit very young people, killing them more than it does, people that are, above about 8 years old all the way until their 50s or 60s. So elderly people, very young people, and poor people, we'll talk about that in a few moments, are kind of disproportionately affected by heat deaths. Number one weather-related killer in the United States over the last 30 years. Now here's a good question. Can the presence of a large city, there's the Chicago skyline there for you, impact air temperature? Well, if you look at how much Chicago, when you put it all in here, there's a population of about 8 million people inside of this little arcing line that I drew here. Those people have transformed the way that this landscape looks. And as a consequence of that, we can have something called the urban heat island. Now, what is it? Well, the urban heat island is caused by these factors. When we put in large cities, we make them out of concrete and asphalt, brick, metal, glass. We have cars which have hot engines, trains, buses, trucks, airplanes, all of which emit a lot of heat. We have industrial-sized air conditioners which take the hot air from inside buildings and put it outside as they cool the air on the inside. We have factories releasing a lot of heat. And the buildings in large cities act as giant canyons. They focus heat down toward the ground. And what's the point here? Because of the construction material of a city, the fact that we've removed vegetation, we've removed soil, well, can give the city a bias toward higher temperatures. Look at this. Minneapolis, Chicago through Milwaukee, St. Louis, Indianapolis, Columbus. Down here in Tennessee, we have Nashville. Coming right up over here, this is Kansas City, Atlanta, Dallas-Fort Worth, Houston. What am I circling? Well, the map you're seeing here is a temperature anomaly map valid on the 17th of July in 2018. Notice how each one of these big cities is. We have higher than climatological average temperatures. So the result? Well, big cities often have temperatures that are several degrees warmer than the surrounding countryside. So that's because the heat is absorbed by the building materials of the city and it's released throughout the day, but the biggest change is in overnight temperatures. When the sun sets, you expect things to cool off, but in the city, all the heat stored in the building materials, you saw me list them off right here, is released overnight, keeping overnight temperatures oppressively hot. So the urban heat island, a real thing for big cities, causing major differences in the temperature compared to the surrounding countryside. Why? building materials. We've used building materials to build the city and replaced what was once there, which is soil and vegetation. Now, why is that important? Well, when the sun beats down on soil and vegetation, nearly half of the energy from the sun goes into just evaporating water out of the soil, evaporating water out of the vegetation. The other half is used to heat it up. You get rid of the vegetation, 100% of the energy from the sun goes into heating up the surface. Now, one of the best examples of this was the 1995 Chicago heat wave. This heat wave hit in July, taking temperatures way, as you can see in the chart here, way up above 90 into the hundreds. In fact, one day peaked at 104 degrees. On that day, the dew point temperature was in the 80s, giving the heat index of 120 degrees Fahrenheit. Now, the thing is that Chicago has a heat emergency plan, but it was not used because during this time in July, most of the city's politicians, leaders, were all on vacation. And who did this particular heat wave affect the most? The elderly and the poor. Many of the deaths, of which there were nearly 1,000 reported in the Chicagoland area, were from poor people living on the south side. And that was because you're poor, you can't afford you can't afford air conditioning, and you can't afford the air conditioning. And as a consequence, well, imagine sitting in a room at night, locked doors because you're afraid of getting robbed. Maybe in a place like Cabrini Green on the south side of Chicago before they took it down. And you're sitting there, you're elderly, you have problems like asthma, you have other heat-aggravated illnesses, and all you get is to open the window maybe. There's no air conditioning unit in it. The temperature inside your small apartment is stifling, maybe approaching 90 to 100 degrees. No movement of air. People were found dead in their apartments because of this. And it was incredibly tragic because Chicago has a heat emergency plan. The heat emergency plan was there but not used. But remember, the worst time that the urban highland has its effect is overnight. Now, what causes them meteorologically? Well, what we see here is that we have large ridges in the flow of the jet stream. That's where the jet stream kind of bends to the north, just like this. When this occurs, when the jet stream bends to the north like that, heat comes pumping up out of the south, and it makes it very, very, very hot. That's a weather phenomenon we're going to talk about a lot in this video lecture. So remember, the urban heat island effect greatest at night. We expect to get relief during the day. You can go places, you can go to stores, you can get away, you can go to a place that has air conditioning, but at night when those places close, you may not have any options. So what happened? 1999, another massive heat wave hit the city, but the city learned its lesson from 1995 where it lost over 1,000 people. And what it learned was, put their heat emergency plan into action. What does it do? It opens up all municipal and public buildings all day long, 24 hours a day, so people that don't have air conditioning can get into it. City of Chicago gives free bus and train rides during this time because they're air conditioned, allow people to sit on them and stay cool. There's a phone service. You can register a number where you can be called every few hours by this number, and if you don't respond, well, they'll assume that there's a problem and they'll send out someone to come check on you. Because of all this, a similar magnitude heat wave hit in 1999 and only about 100 fatalities out of it. A 90% reduction because they used the plan that they had. Just to put this in contrast, in 2003, a heat wave hit France, killed 70,000 people. This is why heat is so deadly. It affects everybody. And that is why we have to learn about how the weather patterns come together to produce drought and deadly heat waves. All right, let's get back into drought here. Because understanding drought is all about monitoring precipitation, I'm going to tell you how we do it, okay? We do it primarily with Doppler radar, which you see down here is a picture of a Doppler radar, and a tipping bucket. It's kind of a neat device. When it rains, the rain comes into this funnel right in through here. And it's funneled in there by, see this thing in the background here? I got it kind of outlined over there. That funnel that's in the background there sits on top of this whole device. And again, the rain comes in like this and fills up this, this little seesaw-looking bucket. When it fills up this side, the bucket tips and pours out the spout, but this little piece of metal right there touches this piece of metal, completing a circuit. And when it tips this way, it records 1/100th of an inch of rain. And it tips back the other way, because when it tips, it'll fill up the other side. It records another 1/100th of an inch of rain. It goes back and forth, telling us how much rain fell in a particular location. That's a point source measurement. Radar gives us this radar beam that measures across an entire area. With our rain gauge network and with our Doppler radar, we've been able to make maps like this, showing you what precipitation, average annual precipitation looks like across the country. Where we live right here in Champaign, Urbana, it's about 40 inches of rain a year. But you can see that as you get closer to the Gulf of Mexico, you have your bigger rainfall amounts. The wettest places, though, in the United States are right here in coastal Oregon, Washington, and California. We'll talk about why in a few minutes, but there's some pretty strong onshore flow there. So we have to monitor precipitation. That's the first part. We also have to monitor the lack of it. We do that with the drought monitor. Now, the drought monitor you're seeing here is from way back in November 29, 2016, when a massive drought due to a huge ridge in the flow of the jet stream, just like this, set up over the southeast. And again, we'll talk about that ridge in a few moments. You see, the drought monitor has these classifications that are right here. You notice how they're very kind of nondescript. Abnormally dry, moderate drought, severe drought, extreme drought, exceptional drought. Why do we use these kind of broad descriptors? Because drought is region specific. There's no formal definition. So we got all the way to the 4th stage of drought. Technically, it's the 5th because we start at 0, but the D4 stage of drought in this section of the country down here in the southeast. And when that happened, well, a very popular tourist destination called Gatlinburg in Pigeon Forge caught on fire. And I'm using these images with permission here, showing you what happened when the fires raced across Gatlinburg. That's an SUV where, due to the fire, which was set by 2 boys, but fueled by the drought, reached 1,200 degrees Fahrenheit. These are puddles of aluminum. From airplane, one of my students sent me this great picture here. You can see the smoke plume carrying downstream from the massive fires in the mountains of Tennessee and parts of Alabama, North Carolina, that region. So the drought monitor told us that it was susceptible to having this. The fires came through and just burned everything. All right, so what is the drought monitor? Well, the drought monitor you're looking at in the upper left-hand corner, there's from July 12th, 2018. Okay, so this will be our example we're going to use. It's based off of something called the Palmer Drought Severity Index. And that is a regional index, which is based off of a supply and demand. What supplies the water? Groundwater. What supplies water? Precipitation. So those are our 2 big supplies. Runoff, use, and evaporation gets rid of it. So when we see an imbalance between the supply and the demand, well, we can then turn that into the Palmer Drought Severity Index, which is negative when things are in drought and positive when things are in flood, and make a map out of it. So this is a map of the drought monitor, which is made at the University of Nebraska-Lincoln. Now, what's neat is we can watch how the drought monitor changes. Well, right now, when I'm making this video, which is very near July 12th, we had massive drought in the Four Corners region, drought running up the west coast of the United States, and drought that has been getting relieved here in the Central Plains, but developing in parts of Louisiana and Arkansas. How do I know that? Well, look at the map below this, or both of the maps below this. This is looking at the change in drought over the last 2 months. So when you see these colors in through here, we're seeing degradation of drought. And when you see here, this is improvement. Now, over the last couple of months, this map shows you the percent of normal precipitation flow. So 100% to this side is wetter than average. That's up to 200% of normal. And back down to 0 is over here. Look at this. Very dry here, where we have a lot of drought. But notice that the drought has been improving in this region because that region got a lot of precipitation. It's getting worse right in through here, where they've not been getting the precipitation. You see, this is how we do this. We monitor the supply versus the demand. And we put it all on a map called the drought monitor map. So hopefully that makes some sense to you. Now I want to talk about California. If you like to eat fruit and vegetables, you need to pay close attention to California. And that's because in the United States, California leads the nation in the production of over 40 different fruits and vegetables. So if you like strawberries, broccoli, the list goes on and on and on and on, including a bunch of nuts as well here, okay? And milk. California leads the nation in the production of those fruits and vegetables. Now, I'm showing you here a location in the Central Valley of California. And the graph you're looking at goes from 2012 to 2017. See this top line? This top line represents how we should accumulate precipitation, cumulatively, okay, from 2012 to 2017. What they got? Down here. During that time period, they built up a major deficit in precipitation. They lost 60 cubic kilometers of groundwater from their aquifer due to irrigation. I talked to a farmer there who was trying to dig a new well, To dig a new well to irrigate his farms, he had to go 2,000 feet deep before he hit it. His farm was subsiding into the ground because of the groundwater loss. We could actually measure a shift in gravity in this region because of the loss of groundwater. And all of this was because of a prolonged drought in California. You see, California is the subject of some intense studies right now. We're learning that California has is experiencing what we're now calling the California whiplash, where it goes from major drought to major flooding. And the cumulative drought that you saw here increased grocery prices across the country because of, well, the lack of these different fruits and vegetables, which were not easily grown because of the drought in California. What solved it? Well, from October 16th to March of 2017, 45 separate, strong onshore flow events ended a 5-year drought. In California, they received 90 trillion, that's trillion with a T, 90 trillion gallons of rain from October 2016 to March 2017. And what did they get them from? They got them from these features. We call them now generically atmospheric rivers, but that's the flow of the jet stream. Now let me show you something. Do you see right over here? Look at the mouse. Right over here, that's a ridge. See this broad elongated dip south? That's a trough. And this atmospheric river picks up moisture across the Pacific and it slams into the west coast of the United States. And there's a mountain chain all along the west coast. The air is forced to rise over the mountains where it makes clouds and precipitation and snow. And 45 separate strong onshore flow events created this, well, 90 trillion gallons of rain for parts of California, ending a 5-year-long drought. But I'll tell you something. You saw a few moments ago, even after all this rain, California is back into drought again. And that's why 40 million people live in California. They use a lot of water. And combine that with the climate sensitivity of that region, well, we got the California whiplash. Drought, flood, drought, flood. Atmospheric rivers bringing in the flood. Lack of them brings in the drought. Just to show you here, California in that year 2017 almost had its wettest year on record. We had at one point over 300% of normal snowfall in the Sierra Nevadas. Just 3 years before this, they were at nearly 0% snowfall in the Sierra Nevada mountains. Incredible to see the changes there. So that brings me to a question I want to ask you. When does drought typically start in the western United States? Now, the answer to this is winter or spring. And that's because it's during winter, primarily during winter, that California and much of the western United States gets its snowfall. And it's the melting of that snow that the western United States relies on for hydroelectric power, for irrigation waters, and the waters to fill their reservoirs and the river systems. It's snowmelt. It's a completely different regime than we have over here in the eastern half of the country. So because wintertime is the wet season for the West, it's all about those rains and those snows not coming that give us drought. In the eastern part of the United States, it's spring and summer. Our wet season is spring and summer because that's the time of year we get our thunderstorms. And therefore, if those thunderstorms don't come, we settle into major drought. So I just want you to know the difference between the western part of the United States on the western, basically western of the continental divide, and the eastern part of the U.S. All right, so here we go. Pay close attention to me here. I'm going to talk about weather patterns that cause drought. We're going to talk first about the high over low pattern, also called the omega pattern. It gets its name because it looks like the Greek letter omega. You see, along the west coast, they fear the high over low omega pattern in the jet stream. Now, what is it? It's where you get the flow of the jet stream going into a huge ridge. There's that word again, a huge ridge. See it here? Into British Columbia, and a deep trough over California or the Baja. When that happens, all the storms are diverted away from the west coast. They go to Mexico or they go to Canada. And you end up getting this flow that is, instead of being onshore, it's now offshore. And there's a giant desert here, and therefore it's incredibly dry. We had a big ridge in the jet stream here in the 2010 Winter Olympics because that they couldn't get snow in the mountains. So it's all about these ridges, okay? Omega pattern looks like the Greek letter omega. See it there? Now, when that pattern sets in, well, people in California know to fear high air pressure over Nevada. Now, remember what we've learned. Air flows out of a high pressure system and circulates clockwise. Now, why does that matter? Well, that gives you this offshore flow. See the air coming from Nevada through California? And when that happens, check it out. Air descends over Nevada, goes over the Mojave Desert, which is here, rises over the San Gabriel Mountains, and then descends on the back side, giving you this wind we call a Föhn wind or a Santa Ana wind. Now, what does all this mean? Well, the air is already dry in the desert. Any moisture that is in it is squeezed out as it goes over this side of the San Gabriel Mountains. So that would be this side over here. And then it goes racing down, compressionally warming and drying out, and it goes racing over the LA basin. And when that happens, well, the relative humidities can drop down to single digits, and it dries out the vegetation in days. Doesn't take much. And if, a would-be discarded cigarette or a campfire that wasn't put out, if the embers for that catch fire to the mountains that surround and the forests that surround LA, well, look at that map that you see in the upper right-hand corner. That's the smoke plumes from some massive fires due to the Santa Ana winds. These winds, again, race down the sides of the mountains, sometimes at speeds over 60, 70, 80 miles an hour. They are exceptionally dry. And any of my students right now watching from California know exactly what I'm talking about. And as they go racing across here, well, the humidities are so low, dries out the vegetation, sparking, fires. And by the way, if you go there, even though the temperatures can be approaching 100 degrees, you can get a cold because it dries out your nasal passages in your throat so easily because it's so dry. That's what happens when the omega pattern sets up offshore flow through California. So here it is. This was 2017. Do you see the omega pattern? Let me show it to you here. Here comes the flow. Part of it shifts north into a huge ridge. I just drew it for you there, deep trough over the Great Lakes. The other part of it diverted to the south, just like this. That's the omega pattern. See it? When that happened, we had a few of our billion-dollar disasters from 2017, including these massive fires here in the Pacific Northwest. Let me show you what they look like. Satellite animation here. See each one of those big plumes there? That's smoke plumes rising from the fires. That's not clouds, that's smoke plumes. Now, there are some clouds that actually sit on top of it. You can make a cloud type called a pyrocumulus that forms on top of a rising smoke plume from a fire here. But what I want you to see is the smoke. In Illinois, we had some of those brilliant sunsets in June and July of 2017 because we looked westward as the sun set into all this smoke. And the smoke filtered out all the short wavelength light, like the blues and the greens, leaving us only the yellows, the oranges, and the reds. And I'll tell you something. When you see brilliantly red sunsets, deep, deep red sunsets, the air quality is poor. Something to think about there. All right. East of the Rocky Mountains, we watch out for something called the Death Ridge or the Bermuda High. Yes, that's what we call it, the Death Ridge. Again, look at this. When we get a big dome of heat building in the central or eastern part of the United States, the flow of the jet stream goes around it, bulging north. Again, there's that word ridge. We had this in summer of 2012. We also had it in fall of 2016 over the southeast. You saw that a few moments ago when I showed you that fire there in Gatlinburg, Tennessee. So it's all about ridges. This is the type of weather pattern that farmers fear the most in Illinois. When the jet stream does this, builds into a huge ridge here with troughs on either side. What are troughs? Well, that's where the jet stream dips south. Troughs are cool and wet. Remember that. Troughs are cool and wet. Ridges, hot and dry. Storm systems are diverted into troughs and around ridges, which means we don't get rainfall. And this is what happens. You see the flow around a ridge like this. This is June 2016. The flow around a ridge like this not only caused major, major heat. We had a massive heat wave, heat advisories, heat warnings out for a big section of the country. But it also caused some major problems with transportation. Here's a screen capture of a video I want you to watch. See that car there? You're right. That car is airborne. And that's because 100-degree heat in Minneapolis-St. Paul caused the road to buckle underneath it. And this person did not see it and hit this going about 70 miles an hour and actually flew about 20 feet before landing right here. Definitely check out this video, which I'll post at the end of this lecture. So this is what the heat can do under those domes, those big giant ridge domes, okay? All right, I'll give you another example. This was back in July 3rd, 2003. Now this is how I like to look at weather data. For everybody else, this is the flow of the atmosphere. See the dominant high pressure, the huge ridge in the jet stream? Well, we had persistent ridging like this for a long time in July and August 2012. And this is what our corn looked like. That's my hand. I'm holding an ear of corn that's about 25% of what it should be. That is why the price of corn jumped in 2012, like we talked about at the beginning of this lecture. That's what we were getting out of Illinois. And if Illinois or Iowa don't make their corn yields, well, just remember this. If Illinois and Iowa became the country of Illinois and Iowa, we'd be the third largest grain-producing country in the world. Therefore, the world watches our corn and soybeans because if we can't produce them, the world's going to suffer. And in 2012, it certainly did because our production was so low due to these massive ridges. All right, what I want to finish with is I want to talk about some major drought in U.S. history. We've talked about the drought of 2012. We've looked a little bit at that drought in 2016 that caused the fires in Gatlinburg. And we talked about the drought that we had over the last 5 years or so in California. But before that, one of the worst was the 1988 drought. When it happened, this one-year drought, which cost $44 billion, was the most expensive weather disaster of all time. Now, since then, we've had Hurricane Katrina, we've had Hurricane Harvey, other major weather disasters. But up to that point, most deadly. Most deadly, but most expensive. Now, what you're looking at here is the Mississippi River in Tennessee. It was so low, they shut barge traffic down, and people went out and started collecting things that were once submerged that were now being exposed because the river wasn't there. Oh, and Yellowstone burned down. 1988, decades long of poor fire management practices combined with a massive drought caused this major eruption of fire in the Yellowstone. That's what heat can do when you have Palmer Drought Severity Index values that are off the charts low. Remember, positive values flood, negative values drought. And look at the drought and its extent. July of 1988. One of the worst single-year droughts in U.S. history. And you better believe it, every farmer across the country uses 1988 as its benchmark, as the worst drought they've ever had. Now, going back farther, in the 1950s, we had a drought event that set up in Texas. And during that time period, 244 of the 254 counties in Texas were declared natural disaster or federal disaster areas. The rain just shut off. And when it shut off, one of the big problems was Texas, heavy agriculturally productive region. Well, for a decade, they had major problems with rainfall. And as a consequence, their groundwater levels dropped 50 to 100 feet. And this is what changed in Texas. I got a Google image here that takes you to northern Texas in the Panhandle near Amarillo. Had I shown you a similar image like this before the 1950s, if we would have had one, every one of the fields that you would have seen here would have been rectangular. But because of the drought of the 50s dropping the water levels 50 to 100 feet, we had to actually change the way we do farming. You see, at the center of every single one of these circles, it kind of looks like a Pac-Man convention here, is a pivot head for irrigation. To do production agriculture in Texas, because of the change in climate in this region, they have to irrigate. And here's something that's really important. Brand new research that was released in 2018 is showing that the aridity index, that's a measurement of how much moisture is in the atmosphere, has been changing along the 100th parallel. Now, where's that? It kind of runs right up the center of Texas, near Texas. We are seeing the drying out of the land region between the Rocky Mountains and kind of the central part of the United States. That's a major climatic shift, which is changing agriculture in the middle part of the country. But where I want to finish is probably with the weather disaster that has shaped U.S. history the most. It is currently considered the worst natural disaster in U.S. history ever. Now, I know Katrina was the most expensive, but this hit many more people in a much larger area, and it lasted for nearly a decade. And it happened during the Great Depression. The Dust Bowl, a massive climactic shift that lasted a decade, hitting us at a time when we were already socioeconomically having problems. And when it occurred, it hit the middle part of the United States very hard. You see, for about 10 years, we had a shift in ocean temperatures across the Pacific Ocean and some other global changes. And it just got drier than average. And it compounded and added up. And the rain basically stopped right about the time that the stock market crashed in 1929. So at the same time of having major economic problems, we had no rain hitting our breadbasket. And it was a very, very tough time in U.S. history. Now, when this came through, well, we're still looking at records set in the 1930s. They've held up all the way to, this time period here in the the second full decade of 2018. So, when it says here, though, that this was due to both weather conditions and human influences, I want to talk about the very poor land management that led to these massive, massive dust storms. Hence the word, or the name, the Dust Bowl. Now, what did the Palmer Drought Severity Index look like? Well, it was nearly off the charts for a big section of the country. And that's all this graphic is showing you here. Drought was widespread. We had a decade of well below average precipitation. And this was right in the middle part of the United States. And that led to these massive, massive dust storms. Now, why were they there? Well, let's kind of take a look at some pictures of them. I don't know if you've ever been in a dust storm, but they are incredibly scary. Check this out. Here is the answer. You see, there was some really, really poor farming practices. Believe it or not, people once thought that every time it rained, if it rained during a time of drought and you didn't have a crop in the field, that you should go out and plow your field. Now, what's the problem with that? Well, the idea was plow the field so you can take the saturated topsoil and turn it over to store the water in the ground. That does not work. That's not scientifically proven. In fact, there was a lot of bad science at this time. Believe it or not, there was something called the U.S. Timber Culture Act that told farmers that if you were in drought, just plant a row of trees. Planting trees will all of a sudden bring rain. That doesn't work, but that's what we thought back then. But when you look at this, do you see the rows here that this farmer probably plowed? Well, every time you plow a field, you break the dirt up into smaller and smaller and smaller granules of dirt until finally you could plow it so many times it's dust. Winds come up and pick that up. People thought, when you're in drought, plow the field. They were even told, rain will follow your plow. It does not work that way. So the combination of a meteorological set of events, the below average precipitation, and poor land management led to these massive, massive dust storms. And my favorite story to tell you out of it is this one. In the 1930s, there was a delegation sent from Kansas to Washington, D.C. to beg for money. When they got there, they met this guy named Hugh Bennett. Hugh Bennett was a major proponent of using our land wisely. And while he was there, this delegation got an audience with Congress. And while Hugh Bennett, representing this delegation, was talking to Congress, this is what happened. You see, here they are in Washington, D.C. Hugh Bennett is now just going on and on and on in a special session called by Congress where he's going on for hours telling them how they need to send relief to the middle part of the country. But remember, the United States was a much bigger country then, not in size, but in terms of communication. People in Washington, D.C. couldn't get to the Midwest in, 3 hours to see how bad things were. There wasn't television. There wasn't mass communication. They didn't know how bad it was. This delegation was there to tell them about it. Well, while they were there and Hugh Bennett was giving his talk, Congress didn't care. They had bigger fish to fry, according to them. They were having a major socioeconomic crisis with the crash of the stock market in the 1930s were one of the darkest time periods in U.S. history. So Hugh Bennett is standing literally on a soapbox, preaching, screaming to this audience, which is Congress, and they've all fallen asleep. In the middle of his speech, one of his aides comes up to him and tugs on his shorts, or not shorts, but on his pant leg, and they say, Hugh, listen, we just got a wire, and what we've learned is that coming toward us here in Washington, D.C. is one of these massive dust storms, one like you saw like this. And it's coming. It's going to be all the way to Washington, D.C. Can you stall? Because they think it'll be here in the next couple of hours. And Hugh Bennett, standing there in front of Congress, slowly begins to build in his rhetoric, getting louder and louder and louder. And finally, after 2 hours, reaches this climax, shouting at Congress, waking them up. And he does it perfectly timed, because when Congress wakes up and stares out the window, they start to see massive dust storms like these that you've just seen in these pictures. One massive dust storm, a black blizzard covering Washington, D.C. And they all go racing to the window. And as they get over to the window, Hugh Bennett stands behind all the congressmen who are staring out, who've never seen massive dust storms like this, seeing their city blanketed in dust, seeing the sun blotted out. And Hugh Bennett says, look, gentlemen, there goes Oklahoma. And that's all that it took. 2 weeks later, the Soil Conservation Agency was born, and massive amounts of relief poured into the middle part of the country. Unfortunately, before that, mass migration. 20% of Oklahoma moved to California because of this. But that's one of my favorite stories to tell. Now, what causes these massive dust storms? Look at this. Look at how much dust was blown around here. They say that the black blizzards could sometimes blow, well, in total, blew 50 million acres of dust. That's the entire size of like a state like Kansas. Blew 50 million acres of dust away. Well, let me show you how they can happen. I'm going to explain to you what's called a haboob. Check this out, okay? Massive thunderstorms like this blow up all the time across the Great Plains and across the mountains, but they're often very high-based storms, meaning that they're not close to the ground. They produce rainfall, but often that rainfall evaporates before it hits the ground because the air near the ground in the desert is very, very dry. But there's still a downdraft, and that downdraft, when it slams into the ground, well, spreads out horizontally, and if the ground is dry, it kicks up a lot of dust. Now check out this animation. This is not of a haboob, but it explains exactly what I'm talking about. Do you see this ring kind of emanating from the thunderstorms here? Watch this again. Thunderstorms erupt. Now this is near Memphis, but it's a good example here. They put down a downdraft and look at it racing out. I can't believe we got this imagery here in the middle of July 2018. It's beautiful to see this. I stared at this for actually about 30 minutes just watching it over and over again. Well, along the leading edge of that outflow is where you get dust like this kicking up. That's a haboob. And that dust can race at times at 60, 70, 80 miles an hour. And we get these all the time in the desert Southwest. But some of these, during the Dust Bowl of the 1930s, made it all the way over to the East Coast. And this is a picture of one of those black blizzards, one that came from South Dakota, racing across the country. Now, in addition to them, you can get synoptic level winds that cause dust storms as well. Those are big, broad-scale winds that just happen over over a much larger area. But the haboob is formed from a decaying, dying thunderstorm's last effort to put down a downdraft. And as it does so, it kicks up dust that races across areas, covering everything in inches of dust and blotting out the sun. This happened for a decade in the 1930s, making the drought, or the Dust Bowl of the 1930s, the most influential weather event in U.S. history up to this point. So that's it. That's drought, the largest, the longest lasting, and the deadliest form of weather on Earth.